Alright, the fundamental theorem of algebra is that if you have a polynomial and the degree of that polynomial is at least 1, greater than or equal to 1, then you will have at least one complex zero. Furthermore, whatever the degree of the polynomial is, that will determine how many complex zeros you have. So a complex zero means that the zeros could be they could be real numbers. They could also be imaginary numbers. Okay, so you could have, things like a plus bi, 2 plus 3i, something like that. They could be zeros of your polynomial. So those count as complex zeros, even if they're imaginary. So whatever the degree of the polynomial is, that is how many zeros you will have. Here are a couple of examples of factoring a polynomial completely and then using that to find all the zeros. Whenever the directions are to simply just find all zeros, you have some options. If the polynomial is something that you feel confident that you can factor, go ahead and just factor it. And then you'll have the factorization, set that equal to 0, and then you'll be able to find your zeros from that. Another way is to graph this and then look for the x-intercepts and then do synthetic division. So I'm going to do the same problem a couple different ways just to show you that you have those options if it's something that you can factor. So I'm going to do this first by factoring, and that is I'm going to factor this by grouping. Okay, so in my first group I'm going to take out an x squared and I would be left with x minus 3. In my second group I'm going to take out a positive 1, and again I would be left with x minus 3. Because I have the same thing left behind in each group, that's going to give me one of my factors, x minus 3, and the other factor would be my two GCFs, x squared plus 1. So if I was trying to find all zeros, I would set this equal to 0, and then at that point in time I could set those equal to 0 and solve them. I'm going to show you how to get to that exact same step. I'm going to before I find the zeros, I'm going to stop and I'm going to do this a different way, just to show you how to get to that same step using a different method. If I was not comfortable with factoring this, what I would do is graph this. Okay, so if I graph it, have it graphed here, what I want to look for is x-intercepts. So I see that I have an x-intercept at 3. So what I'm going to do is I'm going to do synthetic division with 3. So I've got 1, negative 3, 1, negative 3, and I'm going to do synthetic division. If I do this, I get a remainder of 0, which is good. That's what I want. That 3 that I did synthetic division with, remember that gives you a factor of x minus 3. And then since this was x to the third, I did the synthetic division once. I'm down to x squared, so that means I have 1x squared. I do not have an x term, and my constant is 1. And I end up at the exact same place, regardless of if I know how to factor, or I can just look at the x-intercept and do synthetic division. Either way, I get to the same place. So with both of those methods, I now need to set these equal to 0 to solve. That is the complete factorization. Okay, so part B, that's kind of what you wanted to show there, is you've factored it completely. To find your zeros, you then just set those equal to 0. So I would get x equals 3, and then I would get x squared plus 1 equals 0, which means x squared equals negative 1. So to solve that, I take the square root, and I get x equals positive and negative. The square root of negative 1 is I. Regardless of which method you choose there in terms of factoring or synthetic division, you should be able to get to a part where you can then just set those things equal to 0 and solve, and we have the answer of 3. We have positive and negative I. My exponent, my degree of my polynomial was 3, which means I should have 3 answers, and I have 3 of those, 3, I, and negative I. Number 2, same directions here, x cubed minus 2x plus 4. Unfortunately, I don't know a great way to factor this, so I'm going to go with my option 2. I'm just going to graph it and look for an x-intercept and do synthetic division. So if I graph this function, I see that it crosses through the x-axis at negative 2. So I'm going to do synthetic division with negative 2. If I do that, I make sure I don't forget my 0 here. So 1, 0, negative 2, and 4. Drop the 1. multiply, add, and we get a remainder of 0, which is good. That means that since negative 2 worked, that I've got x plus 2, and I'm left with x squared plus 2, and I want to set those equal to 0. So that would give me x equals negative 2, which again is our x-intercept, so we should have that right away. And I need to set x squared plus 2 equal to 0, which means we get x squared equals negative 2. We take the square root. We get x equals positive and negative. Square root of 2, I'm just going to leave that as square root of 2, but I can at least take the negative out and make it an I. So plus and minus I square root of 2. The order that you should, when you simplify a radical, the order you should have this is any whole number that you could take out, then the I, then the radical. So if this were something like the square root of 8, 8 is 2 square root of 2, so I would say 2I root 2 in that order. So again, 3 answers because my degree was 3, negative 2, positive and negative I root 2. We have our 3 answers there. Last thing here is just a zeros theorem, which is what I was talking about before. Every polynomial of degree greater than or equal to 1 has exactly n zeros. Assuming that if a 0 has a multiplicity more than 1, you count it that many times. So if I had a 0 twice, again, hopefully you know what that makes the graph look like at that 0. We count that 0 twice in terms of counting up all of our zeros for our polynomial.